morning. So let's keep work on the instantaneous center of velocity, or we just call it instant center. So our midterm is next week, next Wednesday, just to remind you. So the content will include from mobility and graphical analysis and instant center. If we have time to cover the next part, it's called computational analysis, then if we manage it to include that in the in our Wednesday lecture, then that part will also be included in the midterm. Only a few of them. Well, let's see our progress. Okay, so so last week we talked about the different type of instant centers. Just to give you a quick review. So definition of instant center is if we find two bodies, we find a point common to two bodies, and that point at that instant, only at that instant, they have the same velocity. So there are two definitions, but these two definitions actually means the same thing. One is if you can find let's say if we have two bodies, these two rulers, and if we can find a point that these two bodies, they are doing a pure rotational motion. So let's say if right now this moment, well, they are in this position. But maybe next moment, let's say if this point, I point here, that's the instant center, that means they are doing pure rotational motion. So maybe next moment they move to this position. Or they change their position, but the relative motion between these two bodies is relative to this one, and they are doing a pure rotational motion. So maybe you move in this way, then we'll say this point is the instant center. Yeah. But the instant center is not necessarily need to be fixed right at this point. So another case is, well, maybe I'll still move these two together. Maybe they'll all move together here. But the relative motion between these two bodies, they are still doing relative pure rotational motion. But this point can move. So maybe the first moment is here, but with a very small increment, with a very short time, they are moved together in this way. So this point is, they are still doing the same motion. The same relative motion is still pure rotational motion about this point, but this point may move. And this point, no matter is relative to, we say if this one link 2, link 3, this point, let's say is P, and this P is the instant center, and P2 and P3. So if they are doing pure rotational motion, pure relative rotational motion, this point may still have certain velocities. I mean, relative to the global coordinate. This one is their absolute velocity. If they are doing pure rotational motion, then their velocity at this point will still be the same. They can move together. It's very sticky. So as long as this one is still attached, that means they are still doing the pure rotational motion, although this point may move. Yeah. But we need to make sure this point, no matter is to link 3 or link 2, they are moving at the same speed. So they move together. They move here. Yeah. If that's the case, then we'll say this point is the instant center, because they are doing pure rotational motion. And that also means if they are doing pure rotational motion, I mean the relative motion is a pure rotational motion, that means the velocity of this point, no matter we are considering P2 or P3, well, they must be the same. So the two description here, the first one is saying the linear absolute velocity of these two constant point. The constant point means the instant center, which is this point we use for these two links. So it must have the same linear absolute velocities. Or another meaning is they are doing pure rotational motion. The two meaning of these two descriptions are the same. Any question for this one? So we went through a couple of cases. For example, it's revolute joint. If these two bodies, they are connected by a revolute joint, then this one, well, they were always doing pure rotational motion about this point, this body B and body C, always. So although it's called instant center, but for this case, it's actually permanent. Yeah. You'll always be the revolute joint. The instant center will always be a revolute joint. And the velocity, IBs, let's say for this case, will be I. No matter you are seeing this point from body B or body C. They must be the same. Well, for this case, for sure, it will always be the same. Another case is the curved slider. So for curved slider, if we there's a body B and body B is the slider, body C is the rail, the track. So if we want to find a point that for these two bodies to doing a relative rotational motion, then it must be the center for this track, because this slider is moving along this track. So if you want to see this slider and this track, they are doing pure rotational motion, then it must be the center for this curvature. And that's another case, similar to this one, but this one right now, the track is a straight line. So if it's a straight line, then the center of this curvature is at infinity. It's at infinite distance. Yeah, it must be in this direction. It cannot be a random direction. It must be in this direction. Yeah, I used an example last time. If a curvature is like this, then we know the instant center is here. But if you flatten this instance, this track, then you'll move up. Yeah, the yellow cross is for this yellow track. And if it's a flat line, then you know it's at infinity. So another example is a rolling. Rolling is very similar to R joint, very similar to revolute joint. Because for rolling, these two bodies, they are doing, there's no sliding between these two bodies. So we know if they are doing pure rotate, if they are a rolling pair, we know this body B must be rolling or must be rotating for about this body C at this point. I think it's pretty much the same as R joint. But the only difference is for this rolling case, this instant center will always change as long as this body is keep moving. Yeah. But right at this moment is just right at the point they are in contact. And they are doing pure rotational motion about this P point. So if they are doing pure rotational motion about this point, then this one is the instant center. Yeah. So the last case we are going to talk about is the CAM. So the difference between a CAM pair and a rolling pair is for CAM pairs, they are doing both sliding and rolling motions. So it's not pure rotational motion. It may slide. It may slide along this direction, but it may also roll about point P. Yeah. So compared with the previous one, this CAM pair has one more degree of freedom, which is in the sliding direction, in the common tangent direction, as for the sliding. So we need to define the instance center for this case. So if we only have these two links, and it's not pinned to the ground or pinned to any other links, actually we cannot define the exact location for the instance center for now. Okay, so first thing is, well, I was saying this one may have sliding, relative sliding, and also rotational motion because it's a CAM joint. How if right now if there is no, it's possible it has both rolling and sliding. Rolling and sliding. So I'll write here. It may have rolling and sliding. So rolling means pure rotational motion. How if this one only have sliding motion? They only have relative sliding motion. If that's the case, then where should the instance center be? If although they can do both rolling and sliding, but it's in a very extreme case, it may only do sliding. If this CAM joint only do sliding motions, then where should the instance center be? Infinity, right? So if it's only sliding, then it's the same as this case. If it's only sliding, pure sliding, they're doing relative motion and sliding along this common tangent. If it's pure sliding, then it's at infinity. So I should just use the symbol. How if it's pure rolling? If it's pure rolling, then where should the instance center be? Yeah. If they are pure rolling, then you are right at this point P, because it will be the same as this one. If it's pure rolling and there's no sliding, then the instance center should be at P. But this CAM joint, it could be the combination of these two. So a very extreme case is if it's pure rolling, it's at this point P. If it's pure sliding, then it's at infinity. But if it's a combination between this combination of these two, then you will be between this point P and the infinity. So that's the only thing we know. We know the instance center for this CAM pair is along this line. But we don't know where it is. We only know it must be on this line. But if it's pure rolling, then it's this point. If it's not, if it's pure sliding, that's it. It's at infinity. If it's a combination of these two, then you will be between this one and the infinity. Infinity can go to this right-hand side, can go to the left-hand side. So if it's a combination of rolling and sliding, we know it's on this line. But currently, we don't know where it is. We need other information to get its final location. Any question for this one? Yes?
How do we determine the positions of OC and
OC and OB. Oh, this OB and OC means the curvature for this cam at this contact point.
It will be given, or we have to?
It will be given. Yeah, for this case, it will be given. We didn't define this too. Yes.
The infinity was like going up and not horizontal, because in the other case that we draw, it would go up and up.
Oh yeah, that depends on the sliding direction. It's perpendicular to the sliding direction. So in this case, it's in this direction because it's sliding along this line. So yeah, the center. Yeah, it's because the slider is here. So if you want to consider this slider and this track, they are doing pure rotational motion, then the center must be in this direction, really in this direction. Because only in this direction, they were doing their velocity could be in this direction. It's a radius, and so that would be the direction for the velocity. Just like this case, it's perpendicular to the tangent of the curvature. Any other questions? So currently, we won't be able to define the exact location for the instance center. We need other information in order to define the exact location for this for the instance center. So the bottom figure is the same cam. So you can see the shape is the same, the shape, yeah. But the only difference is right now we use an R joint to connect this body to the ground and body C to the ground. So if they are fixed, then in this case, we will be able to define the instance center. And here I'm going to write down something to see how we can define the instance center for this case. Let's take a look at this one. Well, it's a bit different from this one. So anyway, so let's say these two cams, they are currently contact at point P. And from the previous explanation, we know the instance center must be on this dashed line, must be on the the line that's common, that's normal to the common tangent. So this one is a common tangent, and this dashed line is, I'll just call it common normal. So we know the incident center must be on this dashed line, but in the previous case, we don't know where it is. We know it must somewhere on this line. Depends on how much rolling and how much sliding this motion contains. So I just random pick one point. I'm saying, well, assume this yellow cross assume this point is the instant center. I just random pick one. And well, no, it's not the instant center, but let's start with this one. If this one is the instant center, then right now, this link C and link B, they are connected to the ground. So I want to define, if this one is the instant center, I want to define the absolute velocity for this point corresponding to C and corresponding to B. Because from the definition of instant center, we know if I can find VIBC, which is the velocity of this instant center on link C, and the instant velocity of instant center on point B, on link B, they must be the same according to the definition of instant center. These two velocities must be the same if I say this point is the instant center. So to find the VIBCC, because this one is the absolute velocity. So right now we have a fixed point here, corresponding to link C. We know VIBC. VIBC is basically omega C times the length here, this orange. VIBC at link C must be perpendicular to this line. And VIBC on link B must be perpendicular to this line. But we know these two must be the same. So obviously, this one is not the instant center, because obviously their directions are different. So we don't need to discuss it anymore. Their directions are different. For sure, they won't be the same. Yeah. Because these two, they must have the same magnitude and also the directions. So we know it's just not a random point on this line. So where do you think the instant center should be? We need to find certain point to make these two arrows pointing to the same direction. Then where on this dashed line could this happen? Could these two arrows pointing to the same direction? If I pick another point, if I pick a point here, where is this one? If I say this one is the instant center, then this VIBC could be or either this direction or this direction. Because it's perpendicular to this one. If I say that's the, so we know this one is not. So for VIB, sorry, let's see. VIBC at link C. If it's right at this point, then we know a direction, well, let's say it's going down. And this one for IBCB, it will also be pointing down or pointing up. Here I just choose pointing down. Yeah. So this point is the only chance these two VIBC C and VIBC B, they will be pointing to the same direction. If you choose any other, they won't be in the same direction. This one is the only point they will have the same direction. So I'm saying this point is the instant center for this Kem pair. Yeah, how do we know this? It's a connection between these two points.
Yeah, but the vertical.
Oh, so it's a dashed line and intersection between this dashed line and this red line. Because previously we know the instant center must be on this dashed line. Yeah, according to the explanation here, we know it must be on this dashed line. But in order to make these two velocity pointing to the same direction, we have only one choice, which is it must lie on this red line. So these two lines only have one intersection. So that's the only possible instant center for this pair.
And how do we know it goes down?
We don't know actually. Yeah. We don't know if it goes down or goes up. Yeah. It can go up, it can go down. Yeah. But any other point won't have the same direction for VIBC and VIBCC and VIBCB. So usually we, for instant center, we usually name that. So let's say this link 2, I changed them to link 2. Previously it's called C, and it's called B. We usually name this instant center according to their links. So for example, between link 1 and link 3, we know this adjoint is the instant center for between link 1 and link 3. So usually just call it I13 or I131. 1, 3, or 3, 1, they're both fine. It means the same thing. I'll just put a smaller number in the front. And this one, I'll call it I12. And this point, I23. Yeah, you can find there's different Kem pairs, but you can see you also use the same way to find the exact location for the instant center. Because first we know if that's a Kem pair, then the instant center must be on this common normal passing point B. It also must be on the line connecting I12 and I13. So eventually we find this I23 is the intersection of these two lines. Any questions? No? This Let's move to the next. Well, this one is just an interesting example. So suppose we have a 4-bar linkage. So it's this one. You just ignore the top chem first. So that's the 4-bar mechanism. So there's an interesting property for this 4-bar mechanism. If we try to find I13, sorry, well, we should discuss this one later because there's information we haven't discussed. I'll go back to this one later. Yeah. Let's see other things first. Okay, so there's a theorem called Kennedy-Ehrenholt. I'm not quite sure how to read this. Anyway, I usually just call it Kennedy's rule. It's in another textbook, you just call Kennedy's rule. So this theorem is helping us to find the instant center for certain mechanisms. For some mechanisms, we can easily, or for some pairs, some instant center we can easily find them. For example, for this one, it's I12. We know the adjoint is going to be the instant center between that two links. So for example, there's adjoint between 1 and 2. So we know this I12 and this I14. This I34, this I23. We define instant center between any two links. So currently we only find 4 instant centers. There are 2 remaining. One is I24. One is I13. Based on our current knowledge, I think we won't be able to find these 2. But there must be a point. According to that point, this link 1 and link 3, they are doing pure rotational motion. There must exist this point, and there must also exist another point, I23, so that link 2 and link 4, they were doing pure rotational motion about that point. But just based on our current knowledge, we couldn't find these 2. Yeah. So we'll use this theorem to help us to find it. The theorem is saying for any 3 bodies in plane motion, we always discuss plane motion, so you can just ignore this. So they'll have exact 3 instant centers. So here what it's saying is, if we have body, let's say we have body 1, 2, 3, then we'll have 3 instant centers, 1, 2, 3, 1 I12, I23, and I13. If we have 3 links, we should also have 3 instant centers. Yeah. Just you pick random 2 between this, among these 3. Then yeah, you should have 3. Yeah. And the rule is saying these 3 instant centers, they must be collinear. So it means they must be on the same line. So this I12, I23, I13, they must be on the same line. We still have here. So it's the same as this case. If you take a look at this one, this I12, I13, and I23, they are actually on the same line. They are all on the same red line. You can see this one as not a perfect proof for this theorem, but well, that's the best I can do. Anyway, so it's saying, well, any 3, so it's I12, I23, I13. These 3 instant centers, they must be collinear. They must be on the same straight line. So if we know this, we can use this property to find this I24 and I13. I think that's the next example. So usually we use this way to see how many instance centers we have already found. Just like keep a track so we know how many remaining we still need to find. So I usually just put 1, 2, 3, 4. That means there are 4 links. So there must be an instance center between each pairs. So there must be an instance center between 1 and 2. So if I find I12, I will just draw a line to connect this point together to indicate I've already found it. Anyway, so let's just try to find all instance centers for this mechanism. So these 4, they are just adjoint, so we can quickly find them. So it's I12 is between link 1 and link 2, 2, 3 between link 2, 3, 3, 4, and 1, 4. So once we found these 4 instance centers, I'll just connect those dots together. So I found I12, I just use a line to connect 1 and 2, and 2, 3, I connect 2 and 3, 3, 4, and 1, 4. So when I take a look over this diagram, I know I still need to find 1, 3, and 2, 4. Yeah. Right now we only have 4 links, so even without this one, I think you know you need to find 1, 3, and 2, 4. But if we have more links, so let's say if I have 5 or 6 links, it's better you draw this one to keep track on your knowns and unknowns. Yeah. So based on the Kennedy's rule, we know this 1, 3 must be on, so 1, 3. We need to find I13. So we know we can I13, I23. The first group I'm choosing is the 1, 2, 3 group. Link 1, 2, 3. I know if I want to find I13, based on current information, right now I know 1, 2, and 2, 3. I know this I13 must be on the same line as this straight line. I can use this known to draw a straight line, and I know this I13 must be on this straight line. Yeah. Let's see. But if I only have one line, let's say if I know I13 must be on this line. Yeah. The 3 must be collinear, so I know 1, 3 must be on this line. But with this line, I still couldn't find I13. So I probably need another line. If I can find a line to intersect with this one, then that would be the I13. So I can set another group. Right now I'm using 1, 2, 3. I can choose any other. Let's say I4. 1, 4, 3. For 1, 4, 3, for 1, 4, 3, another group of 3 links. 1, 4, 3, I know there are 3 instance centers, I13, I14, I34. And I know these 3 points, they must be collinear. And right now I already have 1, 4, and 3, 4. So I can draw another line. I can draw another line. And I know I13 must be on this line and also must be on this line. So this point must be the I13. Any question for this one? found I13. So I13 means at this moment, this link 3 and link 1, they are doing pure rotational motion about this point. Okay, so let's move. So we still need to find 2, 4. I think that's the only remaining. So to find 2, 4, we can use similar technique. We can use 2, 4. Currently we have 2, 4. So we add one more link to this group. You know this group must contain 2 and 4. So you can either use 2, 4, 1 or 2, 4, 3. So here I use I12, I14. It's for the first group. 1, 2, 1, 4, and 4, 2 must be also on this line. Also another group is 2, 4, 3. So I use I23, I34, and I know I24 must be collinear with this line. So I draw another 2 lines with I12, I14, form a line. And another is I23 and I34. And I24 must be also on this dashed line. So after drawing these 2 lines, we can find intersection, and this one is going to be I24. Any question for this one? Yeah.
Does it matter the order? Like I1, 2 is the same as I2?
I1, yeah, that's the same. The order doesn't matter because it just indicates the instance center between 2 bodies. I just prefer to put a smaller number in front, so I think easier for you to keep tracking. So yeah, so that's the same for bar mechanism, but I just use a couple slides to indicate what exactly does I13 mean. So I mentioned that I13 means this link 1 and link 3, they are doing pure rotational motion. I'll just use this one. Anyway. So I13, 1 and 3, they are doing pure rotational about this point. But currently, because link 1 is the ground, link 1 is fixed to the ground. So if I'm saying I1, so what's the velocity of B I13? Either be I131 or be I133. Let's say be I131. We know if we found this instant center, this one is the instant center, this equation must be valid. But what's the velocity of this one? Because it's ground link, it's fixed to the ground. So no matter what happens, this must be 0. It's always be 0. Because 1 is a fixed link. This happens for this case because right now we have one link between these 2 is a fixed link. And yeah, so if it is 0 and this B I133 must also be 0. So the motion, so right at this moment, this motion will be like this. This I3 is rotating about this green point, but only with a very small increment because the next moment it will change its location. But here I kind of exaggerate the motions. But you can imagine, well, right at this moment, this link 3 is rotating about, it's doing pure rotational motion about this point. If you move further, you will just move away. This means this instant. it's doing pure rotation about this green point. But because it's just an instant, so if you keep moving, well, it will just move away. And at this moment, you will need to find a new I13, because it is an instant center, so only happen at the instance. Anyway, so similar to this I24. But because 2, 4, either 2 or 4 are fixed to the ground. So this point can be a moving point. So for this case, VI242, VI244. Well, they must be the same if this I24 is the instant center. But it's not necessary for them to be equals 0, because none of them are fixed to the ground. So for this case, a bit different. These 2 points, they will move. So that's the I24 we found at this moment. So with a very small increment, this point, they need to move together. Yeah. I exaggerate the motion, but I hope it's clear enough to explain this behavior. Yeah. So this link 2 and link 4, they are doing pure rotational motion about this point. Yeah. And this within this very small increment. Yeah. If you keep move further, they will just separate eventually. Any question for this one? The reason we are trying to find instant center is eventually we'll use this one to help us to do the velocity analysis. You will find by using this instant, I'll just call instant center method. By using this method, some complicated case we deal with before can be easily solved by using this method. So yeah, so that's the purpose we're introducing this method. Any questions? Okay, so I think that's it. Yeah, I think it's about to ring. Okay, yeah, we'll do this example next time, and I think we'll also cover a few examples using this instant center method to do the velocity analysis. Okay, so that's it. I will see you on Wednesday.